Hello students, welcome to EPG Pathshala. I am Dr. Aditya Saxena from Department of Physics, Central University of Haryana. Today we are going to discuss about the module Electromagnetic Waves 1 from the paper Electromagnetic Theory. So in this module we will get to learn about the following. Firstly, we'll learn about the wave-like solutions of Maxwell's equations in free space away from charges. Then we'll learn about the propagation of electromagnetic waves in non-dispersive medium and how the velocity of the waves depends on the permittivity and the permeability of the medium. After that, we'll also learn about the propagation of electromagnetic waves in a dispersive medium, a medium in which the permittivity of the medium is a function of frequency of the electromagnetic waves. After that, we'll learn about the electromagnetic waves as being transverse in nature. That is, there is polarization of the electromagnetic waves which is expressed in terms of the direction of the electric field in the plane normal to the direction of propagation. Then we'll understand, or rather develop an understanding about the Stokes parameters in terms of which the state of the polarization of the wave can be expressed. And then we'll come to know briefly about the importance of polarization in astronomical studies. The debate over the nature of light dates back to the 17th century. Huygens and Newton gave competing theories, wave versus corpuscular. The corpuscular theory was in the running for almost 2 centuries because of the prestige of Newton. The wave theory ultimately triumphed because of the work of Hooke, Huygens and Fresnel, Young and others. The final nail in the corpuscular theory was struck by Maxwell, who at the same time showed that the light was nothing but electromagnetic waves. The electromagnetic waves produced by moving particles and oscillating currents. For the moment, interested in propagation of electromagnetic waves away from the sources. That is, that right now we will focus specifically on the propagation of electromagnetic waves away from the source, and also we will focus on the fact that the electromagnetic waves which are moving or propagating away from the source, we'll then find out the Maxwell's equation and we'll show that these can be solved without the introduction of the potentials. So the solution of the Maxwell's equations, which for a material medium can be written as the divergence of the electric displacement vector D is equal to the charge density rho by epsilon, where epsilon is the electrical permittivity. The curl of the magnetic field H is equal to mu naught times the current density vector J plus the partial time derivative of the electric displacement vector D. The third of the Maxwell's equation is given by the curl of the electric field E plus the partial time derivative of the magnetic field induction vector B is equal to 0. And the fourth of the Maxwell's equation is the divergence of the magnetic field induction vector B is equal to 0. Solution of Maxwell's equations. Now let us look at how we can use these equations for material medium and what are the conditions that define these equations when they are used for different material mediums. So when we look at the interface of two material mediums, or for determining the propagation of the electromagnetic waves in material medium, then these equations have to be supplemented by material equations which express the derived quantities, that is the electric displacement vector and the magnetic field vector, in terms of the primary quantities that were the electric field vector and the magnetic field induction vector. Now, if we consider a linear, continuous and homogeneous medium, then the electric displacement vector can be written in terms of the electric field vector by the equation vector D, that is the electric displacement vector, is equal to epsilon times the electric field vector E, where epsilon is the permittivity of the material medium. Similarly, we can write down the magnetic field induction vector B as being equal to mu times the magnetic field vector H, where mu is the magnetic permeability of the material medium under consideration. Now, if we consider a situation where are no sources, and then on using the auxiliary conditions, the Maxwell's equations can be written for such a material medium as del dot E, that is the divergence of the electric field, is equal to 0. This is due to the fact that if we are assuming that there are no sources in the material medium, so the charge density due to such a source would go to 0. Similarly, the second Maxwell equation becomes the curl of the electric field vector plus the partial time derivative of the magnetic field induction vector B is equal to 0. The third of the Maxwell's equations becomes the curl of the magnetic field induction vector B minus mu times epsilon times the partial time derivative of the electric field vector E is equal to 0. Here we see that the term containing the current density J is not there because again of the assumption that we've made above, that there are no sources. And finally, the fourth equation remains unchanged and is given by the divergence of the magnetic field induction vector B goes to 0. So now in order to solve these Maxwell's four equations, we take the curl of the third equation and then use the other curl equation, that is the second equation, and the vector identity that is given by the vector triple product or the cross product of the del operator with the curl of the magnetic field induction vector B, and this identity turns out to be equal to the del operator times the divergence of the magnetic field induction vector B minus the Laplacian operator acting on the magnetic field induction vector B. So doing all this mathematical jugglery, we finally see that the equation number 3 of the Maxwell's four equations that we've just written above takes the form the Laplacian operator acting on the magnetic field induction vector B minus 1 upon V square times the double partial derivative with respect to time of the magnetic field induction vector B is equal to 0. Here V represents the wave velocity and is equal to 1 upon under root of mu times epsilon. Similarly, if we take the curl of the second equation and use the third equation along with the vector identity of the vector triple product involving the electric field vector E, and then doing the same mathematical jugglery that we did above, we finally get the equation in terms of the electric field given as the Laplacian operator acting on the electric field E minus 1 upon V square times the double partial derivative with respect to time of the electric field is equal to 0. So these two equations, one in the magnetic field induction vector and the other in the electric field, are wave equations, and the quantity V, which is equal to 1 upon under root of mu times epsilon, is the wave velocity. Propagation in non-dispersive medium. Now, if we look the general form of these above two equations that we've obtained in terms of the magnetic field induction vector B and the electric field vector E, we know that both these equations have a general form of a wave equation and therefore has two linearly independent solutions. So the simplest form of these wave equation solutions can be given by U is equal to e to the power plus minus bracket open iota times the wave vector k dot the position vector x, where dot represents the scalar product, minus iota times omega t bracket close. Here omega is the angular frequency and the wave vector k is the wave vector, and the modulus of this wave vector gives us the wave number. And if we are considering a non-dispersive medium, then the relation between the angular frequency omega, the wave number k, and the velocity of the electromagnetic wave in the material medium is given by k is equal to omega by v, and this can then be written as equal to under root of mu times epsilon times omega. So we can then further write this as being equal to k is equal to angular frequency omega by c, the speed of light, times under root of kappa times kappa subscript m, where kappa is equal to epsilon by epsilon naught and denotes the dielectric constant of the medium, while kappa m is the relative permeability of the medium and is denoted by mu upon mu naught is the magnetic permeability of the free space, while epsilon is the electric permittivity of the material medium under consideration, while mu is the magnetic permeability of the material medium under consideration. Now, let us restrict ourselves to one dimension for the time being so that the solution is simplified. Then we can write down the plane wave solution as u as a function of position x and time t is equal to a times e to the power I kx minus iota times omega times t plus b times e to the power minus I k times x plus iota times omega times t. And so we can just further write this down as a e to the power iota times k times within brackets x minus vt bracket close plus b times e to the power minus iota times k times bracket open x plus vt bracket close. Here a and b are the two constants that we will need to determine, and k is the wave number, omega is the angular frequency, and v is the velocity of the electromagnetic wave. Now, since we have mentioned that the material medium that we are considering is non-dispersive, so we know that the ratio of omega by k, that is the speed of the electromagnetic wave in the material medium, is a constant and is independent of the frequency or the wave number. So what this implies is that since v is independent of both omega and k, so the general solution for the above wave equation can be obtained by doing a Fourier transform. And from our knowledge of the Fourier transform, it is not difficult to verify that the general solution is of the form u as a function of position x and time t is equal to f as a function of position x minus velocity v times time t bracket close plus g as a function of position x plus velocity v times time t, where f and g are two arbitrary functions that have been used over here for determining or for writing down the general wave solution. Propagation in dispersive medium. Now, if we look at the general solution in terms of the Fourier transform that we have used, then we see that the first term on the right hand side denotes a wave traveling to the right. That is, if we are taking the x-axis as the positive axis in the right direction, then the first term represents a wave traveling in the positive x-axis, while the second term on the right hand side denotes a wave traveling to the left. Here the velocity of the propagation of the electromagnetic wave is given by v, and this is also called the phase velocity of the wave. Now if we consider our material medium to be dispersive, then we see that the velocity of the electromagnetic wave in such a medium depends on the frequency and as well as on the wave number, and hence epsilon and mu, that is the electric permittivity and the magnetic permeability, are no longer independent of the frequency but depend on the frequency. So when we take the Fourier transform of the Maxwell's equation and we write down the Fourier transform of the electric field and the magnetic field induction vector, then we get the equations. The electric field vector E as a function of position vector x and time t is equal to integral over the frequency element d omega with integration limits from minus infinity to plus infinity acting over the electric field vector E as a function of position vector x and angular frequency omega times exponential to the power minus iota times omega times t. Similarly, the magnetic field induction vector B can also be written in terms of its Fourier transform as the magnetic field induction vector B as a function of position vector x and time t is equal to the integral over the frequency element d omega with integration limits from minus infinity to plus infinity, acting on the magnetic field induction vector B as a function of position vector x and angular frequency omega times exponential to the power minus iota times omega times t. Similarly, we can define the inverse Fourier transforms of the electric field vector and the magnetic field induction vector as follows. So the electric field vector, inverse Fourier transform of the electric field vector is defined as electric field vector E as a function of position vector x and angular frequency omega is equal to 1 upon 2 pi times integration over the time element dt with integration limits from minus infinity to plus infinity, acting over the electric field vector E as a function of position vector x and time t times the exponential to the power iota times omega times t. Similarly, the magnetic field induction vector inverse transform is given by magnetic field induction vector B as a function of position vector x and angular frequency omega is equal to 1 upon 2 pi times integration over the time element dt with integration limits from minus infinity to plus infinity, acting on the magnetic field induction vector B as a function of position vector x and time t times exponential to the power iota times omega times t. Now, if we replace the time derivatives in the above Maxwell's equations by minus iota times omega, then we get the two of the wave equations that we had written above as the curl of the electric field vector E minus iota times omega times the magnetic field induction vector B is equal to 0. Similarly, the curl of the magnetic field induction vector B plus iota times omega times mu times epsilon times the electric field vector E is equal to 0. So here basically we've written the two of the Maxwell's equations which involve the curl quantities, that is one equation which represents the Faraday's law of electromagnetic induction and the other equation which represents the Ampere circuit law. So we've written down both those equations, and the time derivative that occurs in these equations has been replaced by minus iota times omega. And then again, following the same procedure and taking the curl of these equations and utilizing the other curl equation, we can then write down the wave equations, that is the resultant wave equations for the electric field vector and the magnetic field induction vector as the Laplacian operator acting on the electric field plus omega square by v square times the electric field is equal to 0. And similarly, the wave equation for the magnetic field can be written as the Laplacian operator acting on the magnetic field induction vector B plus omega square by v square times the magnetic field induction vector B is equal to 0. Propagation in dispersive medium. So having written down the wave equations for the electric field and the magnetic field induction vector for a dispersive material medium, we can now write down the general form of the wave equation for the electromagnetic waves, and the general form of the wave equation is given by the Laplacian operator acting on u plus omega square by v square times u is equal to 0, where over here u represents the fields that are now the solution of the Helmholtz wave equation that is denoted by this form, and the two linearly independent solutions to these Helmholtz wave equation can be written as the vector u as a function of position vector x is equal to exponential to the power plus minus iota times wave vector k dot position vector x, where the dot represents the dot or the scalar product between the wave vector and the position vector. Further, the wave number k is again given by the formula omega times under root of mu times epsilon, and this is equal to omega by v. But here what is important to note is the fact that while the wave number and the plane wave solutions are still given by the same equations as was the case for the non-dispersive medium, but with this very important difference, and that is that the velocity is now a function of the frequency. So we have finally found out the plane wave solution for the Maxwell's equations, and obviously the solutions that we have found out must also satisfy the Maxwell's equations. So that kind of puts an additional restriction on the solutions that we have found out. Here, if we write down these solutions, that is, if we write down the two linearly independent solutions in terms of the electric field vector and the magnetic field induction vector, then the solutions can be written as the solution for the wave equation involving the electric field vector is given by the electric field vector E as a function of position vector x and time t is equal to the electric field vector E naught times exponential to the power iota times wave number k times the unit wave vector n cap dot the position vector x minus iota times omega times t. Here n cap is the unit wave vector, omega is the angular frequency, k is the wave number, t is the time, and the vector E naught denotes the amplitude of the electric field. Similarly, the solution for the wave equation of the magnetic field induction vector can be given by the magnetic field induction vector B as a function of position vector x and time t is equal to the magnetic field induction vector B naught times exponential to the power iota times wave number k times unit wave vector n cap dot position vector x minus iota times angular frequency omega times time t. And as in the case of electric field, similarly for the case of magnetic field induction vector, the term magnetic field induction vector B naught denotes the amplitude of the magnetic field induction, while n cap represents the direction of propagation of the wave or the wave vector. Propagation in dispersive medium. Now, having written down the solution of the Helmholtz equation in terms of the electric field and the magnetic field induction vector, and also seeing the fact that since each component of the fields satisfies the Helmholtz equation, we get the wave number term as the square of the wave number times the unit wave vector n cap dot n cap is equal to mu times epsilon times omega square, and this is equal to omega square by v square. And here we've used the identity that n cap dot n cap is equal to 1 because the dot product of any vector with itself simply gives the magnitude of that vector, and since this is a unit vector, therefore the dot product gives us the result 1. Also, since the fields must satisfy the Maxwell's equation, therefore if we write down the first of the Maxwell's equation, that is n cap dot electric field vector E naught, then this is equal to 0. Similarly, if we write down n cap dot the magnetic field induction vector B naught, that is also 0. So from these two equations, one can conclude that the amplitude of the electric field vector E naught is perpendicular to n cap, that is the direction of propagation of the wave. Similarly, the amplitude of the magnetic field induction vector B naught is also perpendicular to the direction of propagation of the wave. So in other words, what we can say is, or rather the comment that we can make about the nature of the wave is that the electromagnetic wave is transverse in nature. Here, what is important to note is that we have used the identity that if we have to write down, because if we look at the Maxwell's equation, which involved the divergence of the electric field, which in the present case we have put as 0 because we are assuming that the medium does not have any sources. Similarly, the divergence of the magnetic field also gives us a 0. So we have replaced the divergence, or rather the del operator, with the unit wave vector, which then gives us the result that the wave is transverse. Now further, if we look at any of the Maxwell's equations which involve the curl, then what we see is that if we look at the equation which involves the curl of the electric field, that is the Faraday's law of electromagnetic induction, then we see that the amplitude of the magnetic field induction vector B naught turns out to be equal to under root of mu times epsilon times the curl of the unit wave vector n cap and the amplitude of the electric field vector E naught. Here again, it is important to note that for the del operator, we have substituted the del operator with n cap, and for the time derivative, we have used I omega. So in this manner, if we look at this equation, then what we realize is that all the three terms that occur or that define our electromagnetic wave, that is the electric field vector E, the magnetic field induction vector B, and the wave vector K, or the unit wave vector n cap, which denotes the direction of propagation of the wave. All these three physical quantities are mutually perpendicular, and hence again the statement that we had made earlier that the electromagnetic wave is transverse in nature. So since all these three vector quantities are mutually perpendicular, therefore we can introduce a set of three mutually perpendicular unit vectors which are denoted by epsilon subscript 1 cap, epsilon subscript 2 cap, and n cap. So writing down the two linearly independent solutions in terms of these three mutually perpendicular unit vectors, we find out that the amplitude of the electric field vector E naught is equal to E naught times unit vector epsilon 1 cap. Then the amplitude of the magnetic field induction vector B naught is given by under root of mu times epsilon whole times the electric field vector amplitude E naught times the unit vector epsilon 2 cap. Here the electric field amplitude E naught is the scalar quantity. Similarly, if the amplitude of the electric field vector E naught is equal to E naught prime times epsilon subscript 2 cap, where E naught prime is the magnitude of the amplitude of the electric field vector, then the magnetic field induction vector B naught is given as minus of under root of mu times epsilon whole times E naught prime times epsilon subscript 1 cap, where E naught prime is the magnitude of the amplitude of the electric field vector and epsilon 1 cap is the direction in which the magnetic field induction vector propagates. And both these descriptions, which involve the amplitude of the electric field vector and the amplitude of the magnetic field induction vector, denote transverse waves moving in the direction of the unit wave vector n cap. Also, since the flow of the energy is represented by the Poynting's vector, where the Poynting's vector S is given by the electric field vector E cross the magnetic field vector H, that is the cross product or the vector product of the electric field and the magnetic field. Therefore, we can say direction of the flow of energy is along the direction of the propagation of the wave. That is, the Poynting's vector is also directed along the direction of the wave. And the Poynting's vector can also be given by the cross product of the electric field and the magnetic field induction vector divided by the magnetic permeability mu. Now, the physical fields are real parts of these complex fields. Hence, the time dependence is generally given by either sine of omega t or cos of omega t. Polarization. So, given the above description and also the way the flow of energy, which is represented by the Poynting's vector, is defined, we see that the energy flow has a time dependence given by either sine square of omega t or cos square of omega t, where omega is the angular frequency and t is the time. Here now, what is of interest to us is the time average over one period, that is the time average of the energy flow, which is given by the average value of the Poynting's vector, and this is found out to be equal to half times the electric field vector E cross the magnetic field induction vector B star whole divided by mu, that is the magnetic permeability. Here the cross represents the cross or the vector product between the electric field and the magnetic field induction vector, and the magnetic field induction vector star represents the complex conjugate of the magnetic field induction vector B. And this turns out to be equal to half times under root of epsilon by mu whole times square of the modulus of the amplitude of the electric field times the unit wave vector n cap. And similarly, the time averaged energy density turns out to be equal to the average value of U is equal to 1 upon 4 times bracket open epsilon times the electric field vector E dot the complex conjugate of the electric field vector E plus 1 by mu times the magnetic field induction vector B dot product with the complex conjugate of the magnetic field induction vector B bracket close. And this turns out to be equal to epsilon by 2 times the square of the modulus of the amplitude of the electric field vector E naught. Now, if we take the ratio of the two, that is the ratio of the average over the energy flow and the time averaged energy density, then this turns out to be average of the Poynting's vector upon the average of the energy density is equal to 1 upon under root of mu times epsilon. And this turns out to be equal to the velocity of the electromagnetic wave. Thus, in this manner, we see that the ratio of the time averaged energy flow to the time averaged energy density is simply the velocity of propagation of the electromagnetic wave. Now let us look at the phenomena of polarization of these electromagnetic waves. So now if we again look at the wave equations that we have described earlier and we fix the direction of the electric field, that is, if we either take the direction of the electric field as epsilon subscript 1 cap or epsilon subscript 2 cap, then depending upon what is the direction of the electric field that we have fixed, we can then correspondingly fix the direction of the magnetic field also. However, we choose the electric field to describe the nature of the solution. So, for such a wave in which the direction of the electric vector is fixed is called a linearly polarized electromagnetic wave. Now, if the direction of the electric field is along epsilon subscript 1 cap or epsilon subscript 2 cap, then the wave is said to be polarized along epsilon subscript 1 cap or epsilon subscript 2 cap respectively. Elliptical polarization. So, case that we just discussed wherein we had fixed the direction of polarization of the electric field either along the epsilon subscript 1 cap, which if you look at the figure gives a vertical polarization where the arrows represent the direction of the electric field vector, or epsilon subscript 2 cap, which represents a kind of a horizontal polarization according to the coordinate axis that we have chosen, where again the arrows represent the electric field vector. So these two waves that are linearly independent, and the most general wave is a linear combination of these two linearly independent solutions, which can be written as the electric field vector E as a function of position vector x and time t is equal to bracket open epsilon subscript 1 cap times electric field E1 plus epsilon subscript 2 cap times electric field E2 bracket close whole times exponential to the power iota times wave vector k dot product with position vector x minus iota times angular frequency omega times time t. And here the quantities electric field E1 and electric field E2 are in general complex amplitudes of the electric field along the two linearly polarized directions respectively, that are represented by epsilon 1 cap and epsilon 2 cap. However, in case of unpolarized light, the orientation of the electric field vector changes randomly. And the example of such an unpolarized light are natural light, that is sunlight, light from an electric bulb, etc. Now, if the amplitude of the electric field along one polarization direction, that is E1, and along the other polarization direction, that is E2, have the same phase, the wave is still linearly polarized, and the magnitude of the electric field vector E is given by as being equal to under root of E subscript 1 square plus E subscript 2 square, where E subscript 1 and E subscript 2 have been defined above. That is the first linearly polarized direction, denoted by epsilon subscript 1 cap, is given by, if the angle is theta, then theta is equal to tan inverse of the electric field amplitude E2 divided by the electric field amplitude E1, where these two amplitudes denote the electric fields along the two linearly independent polarized directions. Further, if the phases of the electric field E1 and electric field E2 amplitudes are different, then the wave is in general elliptically polarized. And for such a wave, we can write down the wave to be a traveling wave in the positive z direction, and we can give the equation of the amplitudes of the electric field for such a wave as E1 E subscript 1 is equal to A subscript 1 exponential to the power iota times delta subscript 1, and the amplitude E subscript 2 is equal to A subscript 2 times exponential to the power iota times delta subscript 2, where the term A subscript 1 denotes the amplitude of the electric field along the polarization direction of denoted by epsilon subscript 1 cap, and A subscript 2 denotes the amplitude of the electric field along the polarization denoted by the polarization vector epsilon subscript 2 cap. Over here, delta 1 denotes the phase of the first electric field vector, while delta 2 denotes the phase of the second electric field vector, which are basically along two different polarization directions. Then the resultant electric field vector E is given by the linear combination of these two different electric field polarizations and can be written as epsilon subscript 1 cap times A subscript 1 times exponential to the power I iota times bracket open k times z minus omega times t plus delta subscript 1 bracket close plus epsilon subscript 2 cap times A subscript 2 times exponential to the power iota times bracket open kz minus omega t plus delta subscript 2 bracket close. So this equation gives the general equation for an elliptically polarized electromagnetic wave. Circular polarization. Now, if the above equations for the electric field give the electric fields as complex quantities. So the physical fields are given by the real part of these complex fields and can be written as the x component of the electric field, that is the real part of the electric field, is given by A subscript 1 times cos of wave number k times position z minus angular frequency omega times time t plus the phase delta 1 subscript 1, while the y component of the, that is the real part of the electric field, the physical field, is given by E subscript y as a function of position vector x and time t is equal to A subscript 2 times cos of bracket open the wave number k times position z minus angular frequency omega times time t plus the phase delta 2. And if we write down, rather if we substitute these values of the x component of the electric field and the y component of the electric field in the above wave equation, then we can write down the final equation as given by the square of the x component of the electric field by the amplitude of the electric field along this direction A subscript 1 plus the square of the y component of the electric field by the amplitude of the electric field along this direction given by a subscript 2 minus twice of the ratio of the x component of the electric field by its amplitude and the ratio of the y component of the electric field and its amplitude times the cos of the difference in the phase between the two electric field vectors, that is delta 2 minus delta 1, and this is equal to square of the sine of the phase difference between the two electric fields, that is delta 2 minus delta 1, and this equation represents the equation of an ellipse. Therefore, the polarization is referred to as elliptical polarization. However, we see that if the phase difference between the two electric field vectors or the two linearly independent solutions of the electric fields is pi by 2 and the amplitudes of the two fields are equal, then we can say that the electric field E subscript 1 is equal to electric field E subscript 2 is equal to the electric field E subscript 0 or E naught. Similarly, delta 2 minus delta 1, that is the phase difference between these two linearly independent solutions, is pi by 2, and the electric field vector E as a function of position vector x and time t is then written as being equal to E naught times bracket open epsilon subscript 1 cap plus minus iota times epsilon subscript 2 cap bracket close e to the power iota times wave vector k dot product with position vector x minus iota times angular frequency omega times the time t. The two polarization vectors along the x and the y directions give the electric field vectors, while the direction of the propagation of the wave is along the z direction. And in this case, we see that the above equation that we had obtained for elliptical polarization, which was basically the equation of ellipse, after making the amplitudes equal and making the phase difference equal to pi by 2, gives us the equation of a circle, where the physical fields are given by the x component of the electric field E subscript x as a function of position vector x and time t is equal to E naught times cos of bracket open wave number k times position z minus angular frequency omega times time t, and the y component of the electric field, that is the physical field, is given by E subscript y as a function of position vector x and time t is equal to minus or plus E naught times sine of bracket open wave number k times position z minus angular frequency omega times time t. So at a fixed point in space, the electric field is constant in magnitude but sweeps around in a circle with angular frequency omega. So basically this is how we define the circular polarization. In case of an elliptical polarization, what we see is that as the wave propagates along the z direction, the electric field vector then sweeps in a direction perpendicular to the direction of propagation of the wave, that is sweeps in the xy plane and makes an ellipse. While if in case of circular polarization, again the direction of propagation of the wave is along the z-axis and the electric field vector in this case sweeps out an area in the xy plane which is like a circle, hence the name circular polarization. Now, in case of the y component of the real or the physical electric field, E subscript y, the negative sign denotes the rotation of the electric field vector in the counterclockwise direction when the observer is looking into an oncoming wave, while this is referred to as the left circularly polarized light, and in terms of the particle physics, this is said to possess positive helicity. Similarly, if we look at the positive sign, then this denotes a rotation which is in the clockwise direction when the observer is looking into the oncoming wave, and this denotes the right circularly polarized light, and in the terminology of particle physics is said to possess negative helicity. Now, once we've discussed the circular polarization and the fact that it is a special case of elliptical polarization where the two amplitudes become equal and the phase difference between the two linearly independent polarized solutions is pi by 2, we can now use these two circularly polarized waves and they can equally well be used as a set of basic fields. So for this purpose of using them as a set of basic fields, we introduce the complex orthogonal unit vectors which are denoted by epsilon plus minus cap, and this is equal to 1 upon under root 2 times bracket open epsilon subscript 1 cap plus minus iota times epsilon subscript 2 cap bracket close, so that we can write down epsilon plus subscript plus minus cap star dot product with epsilon minus plus cap is equal to 0, where epsilon subscript plus minus cap star denotes the complex conjugate of epsilon subscript plus minus cap, and epsilon subscript minus plus cap denotes the reversal in the sign of the definition that we have defined for epsilon subscript plus minus cap. Further, epsilon subscript plus minus cap star dot product with epsilon 3 cap is equal to 0. So basically here epsilon subscript 3 cap denotes the direction of propagation of the wave. So obviously since the two polarization directions are perpendicular to the direction of propagation of the wave, so the dot product gives us 0. Then another term that we can define over here in terms of these complex orthogonal unit vectors is the dot product of epsilon subscript plus minus cap star and epsilon plus minus subscript cap, and this turns out to be equal to 1. So we can now write down the alternate representation in terms of these vectors, that is, using these complex orthogonal unit vectors we can again rewrite the expression for the electric field, resultant electric field vector, which is given by vector E as a function of position vector x and time t is equal to bracket open epsilon subscript plus cap times electric field E subscript plus epsilon subscript minus cap times electric field E subscript minus bracket close whole times exponential to the power iota times wave vector k dot product with position vector x minus iota times omega times time t. In general, the amplitudes electric field E subscript plus minus are complex amplitudes of the electric field along the two polarization directions, and this represents elliptic polarization. Again, in terms of these complex orthogonal unit vectors, if both the amplitudes, that is E subscript plus and E subscript minus, are equal and have the same phase, then the wave is linearly polarized. And if the amplitudes are different, that is E subscript plus and E subscript minus are not equal, but the phases are the same, then it represents an elliptically polarized wave with the principal axis of the ellipse in the directions epsilon subscript 1 cap and epsilon subscript 2 cap. Stokes parameters. Now, having given the description of the resultant electric field vector in terms of the complex orthogonal unit vectors, and then having discussed the cases for the linearly polarized light, that is the electromagnetic wave, and the elliptically polarized electromagnetic wave, and also defining the complex amplitudes of the electric field, we can now write down the ratio of the semi-major to the semi-minor axis, which is given by the modulus of 1 plus r upon 1 minus r, where r is given as the ratio of the complex electric field amplitude E subscript minus and E subscript plus. So if this ratio of the complex electric field amplitudes, that is E subscript minus and E subscript plus, is equal to r times exponential to the power iota times alpha, the axis of the ellipse is rotated by an amount alpha by 2. Stokes parameters. Now we can determine the polarization of the electromagnetic wave completely in terms of the 4 parameters, that is the two amplitudes that we have described above and the magnitude and the sign of the phase shift. Now, because the phase difference is hard to measure directly, therefore what one does is one employs an alternative description in terms of what are called as the Stokes parameters, and this description turns out to be very useful. So in terms of the electric field vector, the Stokes parameters can be motivated by observing that for a wave propagating in the z direction, the scalar products, that is epsilon subscript 1 cap dot the electric field vector E, then epsilon subscript 2 cap dot the electric field vector E, then epsilon subscript plus cap star dot the electric field vector E, and epsilon subscript minus cap star dot the electric field vector E. These scalar products denote the amplitudes of radiation with linear polarization in the x direction, the y direction with respect to the positive helicity and negative helicity respectively. And the square of the amplitudes is then a measure of the intensity of each type of polarization, that is the 4 polarizations that we have described above. The phase information is then obtained from the cross products. Stokes parameters. In terms of the linear polarization basis, that is epsilon subscript 1 cap and epsilon subscript 2 cap, the Stokes parameters are given by S naught is equal to square of the modulus of epsilon subscript 1 cap dot electric field vector E plus square of the modulus of epsilon subscript 2 cap dot the electric field vector E, and this is equal to A subscript 1 square plus A subscript 2 square. Here the parameter S naught measures the relative intensity of the wave. The second Stokes parameter is denoted by S1 and is equal to square of the modulus of epsilon subscript 1 cap dot the electric field minus square of the modulus of epsilon subscript 2 cap dot electric field, and this is equal to A subscript 1 square minus A subscript 2 square. Here the Stokes parameter S1 gives the preponderance of X over Y linear polarization. Here one may again recall that A1 and A subscript 1 and A subscript 2 are the amplitudes of the electric field along the two respective polarization directions. Then the third of the Stokes parameters, S subscript 2, is given by twice the real part of bracket open the complex conjugate of epsilon subscript 1 cap dot electric field times epsilon subscript 2 cap dot electric field bracket close, and this is given by the equation twice of A subscript 1 times A subscript 2 times cos of delta 2 minus delta 1, or the cause of the phase difference between these two polarization directions. Similarly, the fourth of the Stokes parameters, that is S subscript 3, is denoted by twice the imaginary part of bracket open the complex conjugate of epsilon subscript 1 cap dot electric field times epsilon subscript 2 cap dot electric field bracket close, and this turns out to be equal to twice of A subscript 1 times A subscript 2 times sine of delta 2 minus delta 1 is the phase difference between these two respective linearly independent solutions of the electric field. And A subscript 1 and A subscript 2 give the amplitudes of these two linearly independent electric fields. Here it is important to note that the Stokes parameter S subscript 2 and S subscript 3 gives us the phase information, and the four Stokes parameters satisfy the relation S subscript 0 square is equal to S subscript 1 square plus S subscript 2 square plus S subscript 3 square. and we usually normalize the intensity so that the intensity of the incoming light is unity. An example that we can consider over here is that of an incoming beam of light which is unpolarized. In that case, we can write down S0 is equal to 1, while S1 S subscript 1 is equal to S subscript 2 is equal to S subscript 3 is equal to 0. Polarization in astronomy. Now this is an interesting part of polarization of the electromagnetic waves that we get to see in astronomy. So it is nice that if all of you get acquainted with some of these facts. Light polarization is an important phenomena in astronomy. The polarization of starlight was first observed by the astronomers William Hiltner and John S. Hall in 1949. Subsequently, Jesse Greenstein and Leverett Davis Jr. developed theories allowing the use of polarization data to trace interstellar magnetic fields. Though the integrated thermal radiation of stars is not usually appreciably polarized at source, scattering by interstellar dust can impose polarization on starlight over long distances. Both circular and linear polarization of light from the sun has been measured. Circular polarization is mainly due to transmission and absorption effects in the strongly magnetic regions of the sun's surface. Linear polarization in spectral lines is usually created by anisotropic scattering of photons on atoms and ions. The polarization of the cosmic microwave background, which is abbreviated as CMB, is also being used to study the physics of the very early universe. CMB exhibits two components of polarization: the B mode, which is divergence free like the magnetic field, and the E mode, which is curl free, gradient only like the electric field polarization. The BICEP-2 telescope located at the South Pole helped in the detection of the B mode polarization in the CMB. This may prove the existence of the gravitational waves in our ever-inflating universe, but confirmation is still needed and awaited. It has been suggested that astronomical sources of the polarized light caused the chirality found in biological molecules on Earth. So students, now let us summarize what we have learned in this module. Firstly, we found out wave-like solutions of the Maxwell's equations in free space away from charges. We then discuss the propagation of the electromagnetic waves in non-dispersive medium and find out how the velocity of the wave depends on the permittivity and the permeability of the medium. We next discussed about the propagation of the electromagnetic waves in a dispersive medium. A dispersive medium is one in which the permittivity of the medium depends on the frequency of the electromagnetic waves. The next question that we tackled in this unit was of the polarization of waves, and the polarization is defined in terms of the direction of the electric field in the wave. Then we discussed about the Stokes parameters, in terms of which the state of the polarization of the wave can be expressed, and these Stokes parameters were then defined. Finally, the importance of polarization in astronomical studies was briefly discussed. Thank you.